Hello, this is the first video of the series Description of Motion. From now on, we will learn about the motion of objects through some videos. In this video, we will learn about position vectors. By motion, I mean that the position of the object changes with time. For the sake of simplicity, we will only consider small objects. By small, we do not mean a representative of the actual object. It means that the shape of the object, its orientation, and its size are not important when considering the motion of the object we are interested in. In other words, we consider an object to be approximately like a point, and then consider its motion in such a way that the essential nature of the motion is not impaired. In physics, an object that is regarded as a point is often referred to as a point mass. In this way, the motion of an object can be described as the movement of the position of a point with respect to time. In order to express the motion of an object, we need to use vectors and coordinates to accurately express the point that changes its position according to time. This is called expressing the motion of an object. In physics, the term kinematics is used to describe only the motion, without asking about the cause of the motion. And the cause of a change in the motion is explained by a force. When thinking about the relationship between force and motion, we call it dynamics. In the next few videos, we will not ask about the causes, but first consider only how to describe the motion, and after that, we will learn about the relationship between force and motion. The most basic way of describing the motion of an object is by means of the position vector. In the following, we will consider the object represented by this point and consider a situation where it changes its position with time. You obtain the position vector by taking an appropriate reference point and drawing a vector starting from this point until the position of the object. The vector is given as a function of time because the position of the object changes with time. Time is often represented by a lowercase t. The letter O represents the reference point, and position vectors are usually represented by the letter R. As I said, when time changes, the position vector also changes. Note that although we have taken a reference point here, we can also take another reference point and consider the position vector from there. If we take this reference point, the position vector is given by this vector here. But if we take another reference point, the position vector is given by this one here. So one important point is that the position vector depends on the way the reference point is chosen. When we want to express a position vector, it is convenient to use a coordinate system. A coordinate system is when we have a coordinate axis in addition to the reference point mentioned earlier. The word origin is used to describe the reference point of the coordinate system. For example, if we consider the motion of a ball rolling on a desk, changing its position like this, the motion of the object is basically in a two-dimensional plane. When considering such two-dimensional motion of an object, we use a two-dimensional coordinate system. Likewise, a three-dimensional coordinate system is used when considering motion in a three-dimensional space. This figure shows a two-dimensional Cartesian coordinate system. The reference point is here. The x-axis is in this direction, while the y-axis is in this direction. The position vector is a vector drawn from the reference point to the position of the object. The x and y values of the vector are given by drawing a perpendicular line to the x and y axis, like this. We can use those two values to represent the vector. These are called the x component and y component. Since the vector itself was a function of time, the components are also functions of time. Thus, in two dimensions, the vector can be represented by two components. What this vector component means is that it is a coefficient of a unit vector. Let us consider a unit vector of length 1 in the x direction and a unit vector of length 1 in the y direction, each of which is represented by ex and ey. Then we can think of this position vector as the sum of two vectors, x times ex and y times ey. In other words, it can be expressed as an equation like this. In this way, you can understand that the components of a vector are the coefficients of the unit vector itself. As I mentioned earlier, changing the position of the reference point changes the value of the position vector, but changing the orientation of the xy axis also changes the position vector. This change is called changing the selection of the coordinate system. And changing the selection of the coordinate system naturally changes the vector components. We can change the x-axis to this direction, so that the y-axis is here perpendicular to it. Such an x-axis would change the expression of this position vector, so that the y component is 0 and only the x component is non-zero. For the sake of simplicity, we assume the two-dimensional case, which can be expressed with two coordinates, x and y. But in general, a three-dimensional coordinate system, which requires three coordinates, is used for a three-dimensional motion. This position vector r can be expressed in terms of three components, x, y, and z. How to find the components is not very important at the moment, but simply put, you draw a perpendicular line with respect to the x and y axis from the object's position in the plane. The value defined by the perpendicular line down from here to the x-axis is x. The value given by the perpendicular line down from here to the y direction is y, and the point where the perpendicular line down from here just intersects z is our value of z. Thus, x, y, z can be obtained. If we arrange unit vectors for each of the three directions, x, y, and z, the components of the original position vector can be written as coefficients of the sum of the three vectors. Now that I have explained that the position vector is given as a function of time, I would like to look at one example. First of all, we are now going to consider a position vector, where position is a quantity related to distance, and the magnitude of the position vector gives this distance. The standard unit for distance and length is meter. The standard unit of time is second. Then, for example, we can consider a position vector like this. Time t is p times s. S here means seconds. If p is 1, t is 1 second. If p is 2, t is 2 seconds, and so on. The position vector is now given by the xy components on the plane. The x component is 2p, and the y component is 3p plus 1. It has units of meters. So we can think of a position vector like this. When thinking about what kind of motion corresponds to this object with this position vector, we can consider the case where the time t is 0, 1, 2, or 3 seconds. That is, p corresponds to 0, 1, 2, 3, and if we write down the x and y coordinates at that time, we get 0, 2, 4, and 6 meters for the x coordinates. For the y coordinate, it is 1, 4, 7, 10 meters, and so on. This means that if we take the x-axis and y-axis and graphically represent the position vector, when t is equal to 0, it is like this. When t is equal to 1, it is like this. And when t is equal to 2 seconds, it is like this. So the position vector is changing with time. Since time is a variable that is continuously changing, it is not actually changing at intervals like this, but rather it is a vector that represents the movement on a straight line connecting these points. In this video, we learned about position vectors. We also discussed the use of a coordinate system to represent position vectors and how they are given as a function of time. This is the end of this video. Thank you for watching and see you in the next one.